Okay, so welcome to this series. Welcome back to this series of Laplace transforms. So today we're going to talk about derivatives. Okay, how do you Laplace transform a derivative? Okay, so I'll jump straight in. So so integrate 0 to infinity fraction dft dt. Okay, exponential. I'll just use exponential, right? E minus st dt. Okay, so this is the basic definition of Laplace transforms. And what do we need to do? Okay, so we will need to use integrate by parts. Okay, integrate by parts. Integrate by parts. So what are we going to integrate and what are we going to differentiate? So we're going to integrate this side first, because when we integrate this side, this one will just give us back our ft. When we differentiate this side, we will have minus s come to the bottom, and yeah, it will become quite easy because s is a constant. Okay. So okay, so let's integrate this first. Okay, so I will have a two sides 0 to infinity. Okay, first part is what? We will integrate ft. Okay, exponential what? Minus st. Alright, so and if you notice this is almost just the definition. Okay, maybe I should write it a little bit better. Ay. Okay, never mind. I think it'll be okay. Never mind. Yeah, this is correct. This is correct. Okay, this is what we are supposed to evaluate first. It's not the Laplace transform, but it looks like Laplace transform. Okay, so this is the first part. Then we have to subtract something, right? We have to subtract something. So integrate from 0 to infinity f of t, and then what? Okay, we have to differentiate the exponential side. So the exponential side is if you differentiate this exponential side, you have minus s exponential minus st dt. Okay, now I want you to notice something. You can actually bring the minus s out into the front, and then we'll get a plus s, because s has nothing to do with t, at least not in the way we define it. Alright, we can actually bring this whole thing out. And what is this? This is just actually the Laplace transform of f of t. Okay. Okay, mathcal O. Oh, mathcal L f of t. Okay, so that's very good for us. How do we deal then with the second term? So we try to evaluate f of t going to infinity. Okay, so we'll just evaluate this term under some conditions. So t going to infinity. Okay, let's right arrow. Okay, exponential minus st at t at infinity. Okay, so we just write this out, right? So f of t going t at 0. Maybe we'll just put t at 0. T equals to 0 times what? Exponential minus s times 0, and that is just 1. Alright, so there'll be a I put the s at the wrong side. Okay, so okay, what do we have here? So now we note a few things, all right? Okay, so if f of t, okay, in general, if f of t, like not equal to exponential s of t, something like that, and if f of t is not equals to st, right, then generally speaking, yeah, I don't think f of t will ever be st in our standard, in problems we encounter, so we don't really have to bother. This thing will just drop to 0 unless f of t goes to infinity. Okay, and yeah, f of t should not go to infinity too quickly. That was with the L'Hopital's rule or something. Yeah. Okay, f of t doesn't go to infinity faster than, okay, exponential minus s t, right? Okay, so f of t doesn't go to infinity faster than exponential s of t. So yeah, because if this thing is like going to infinity really fast, much faster than exponential minus s infinity, then maybe this thing doesn't work so well. But for well-behaved problems, when t goes to infinity, f of t is usually bounded, then that's fine. So yeah, so these are some things you got to take note of, and of course s should be more than 0. So these are some things you should take care of. Okay, at least when we derive it, it's more clear, but otherwise it's not as clear where all these come from. So the first term will drop off under all these conditions. I mean, it's a rough idea kind of thing. I'm not doing it as accurately, but it's good enough that this first term actually drops out. Then exponential of 0 will just become 1. Okay, and what happens? Okay, so we'll have this term. We will have derived our Laplace transform of derivatives. Okay, so let's see how much time. Okay, so okay, very good. Now we kind of roughly have a Laplace transform for derivatives, so we can actually sort of think about integrals as well, because it's the opposite, right? So we can think of it. We can think use this transform for integrals, as long as you have some boundary condition. I mean, okay, so you can see that f of t is actually the integral of dft dt, right? So maybe we can swap this around. Okay, swap this around, and we'll have integral dt f of t, right? So wherever you have this dft dt, you will replace it by f of t. Wherever you have f of t, you replace it by integral of ft dt. Now of course you kind of need this you need the value of this integral at t equals to 0. Okay, so I mean that's one way of doing it. It's a very crude way. Okay, sorry, I think I have too many brackets. Okay, so what? Okay, long and short of it, what is this Laplace transform of integrals? I mean, you can do it the really hardcore way, where you try to make this integral ft dt, then you kind of just substitute this in here and you do everything from scratch, but I am not really in favor of that. Okay, so I'd rather just bring this whole thing over to the left hand side, and I divide everything throughout by s. Okay, so I'll just casually put this here, and I will have this thing here as well. And there you go. Okay, I'll take out the s from the left hand side, and this should be the rough right expression. Now, of course, I think there's a more proper way of doing this. There's a more proper way of doing, maybe a more proper way of doing this, as in more rigorous. But I won't go through that. Just to like help you get a feel. There are probably other people doing it on YouTube already. You can go and search them out. But what I want to say is this: whenever you have a derivative, a Laplace transform of a derivative, you have you just put a s in front of this Laplace transform. Of course, you have some initial boundary condition or whatever you have. Excuse me. Yeah, you have some initial condition here. Ft equals to 0. Okay. So that's what you need to have. And then when you integrate something, you just put 1 over s times this integral here. Okay, you can see Laplace transform of f of t. Okay, so Laplace transform of the integral of f of t dt. That's just 1 over s Laplace transform of f of t. And of course, you have this other constant here. Okay. So we can see in Laplace domain. Okay, f of t. So how do you put this? In Laplace domain, integrating means multiply by what? 1 over s. 1 over s. And differentiating is multiplying by s. So this is the key point I want to bring across here. I'm not going to integrate this properly. You can look at the proper derivation, but I just want to give you a rough show that, you know, when you integrate something, you will have this 1 over s. When you differentiate something, you multiply by s. So that's a very important point. And yeah, let me see whether I can get let me see whether I can get you the proper Laplace transform of this integral. Okay, actually, yeah, this more or less makes sense. Okay, maybe I will do it in a more I'll do it in a more what do you call that, proper notation kind of manner. And let's put some brackets here, curly brackets, so that you can see the subscript. Yeah, okay. And let's put f of t here, so that yeah. So this is basically Laplace transform of integral and derivative. Now once you have this, you have very powerful tools which you can use to derive other Laplace transforms. So let's do some examples. So for example, yeah, I think I will just I'll just do this here. Yeah, okay, so now I think the notation is more or less correct. I'll put in an extra bracket at the end, then it's fine. Okay, so of course we have BCs. So let's do some examples here. What is the Laplace transform of t? Laplace transform of t. Okay, so there are a few ways to do this. We can actually substitute t back into this exponential, into this original definition of the Laplace transform. Yeah, we can substitute t in here and then, you know, just do it from scratch, which of course I don't really want to do. But I want to note something. Okay, note this. Okay, the t dt equals to 1. Right? If you differentiate t with respect to t, it's just 1. So what can we do? We can use this method here. Integral of ft dt. So we can use this. Okay. We can use this to actually find out the Laplace transform of t. Okay, so in this case, ft equals to 1. Okay, in this case, f of t equals to 1. Right, f of t equals to 1. So if you integrate 1 with respect to t, what do you get? You just get t. Okay. So let's do integral of ft. So yeah, this is just one example, and that's very important for you as well if you want to have this Laplace transform done properly. Okay, so let's do Laplace transform of 1. We already did that before, and of course we want to integrate 1 with respect to t, and then we just find out the value. This is an indefinite integral. But okay, we are not going to add constants here. We're just going to evaluate this integral at t equals to 0. Okay, so if you have integral of 1 with respect to t is just t, right? Integrate 1 with respect to t is just t, and t at t equals to 0 is just 0. Okay. So there you go. Okay. What's the Laplace transform of 1? What's the Laplace transform of 1? Yeah. Let's see, how much time? Okay, Laplace transform of 1, we can just go back. We did it before already. 1 over s. Okay, so we just have 1 over s. Okay, that's the Laplace transform of 1. And then we can use this to find that the Laplace transform of t is basically 1 over s squared. 1 over s squared. Okay. So basically, if you have t squared, t cubed, you can always just use this thing. Okay, you can keep using this integration formula again and again and again. It's kind of playing cheat, but it is what it is, you know. Okay, so maybe I'll do a few more examples. Maybe t squared, t cubed, yeah, just to help you get the hang of integrating t. Okay, so let's do Laplace transform of t squared. Laplace transform of t squared. So what is this? So we can use this formula again. Let's use the integration formula. Okay, Laplace transform of t squared. Okay, so what is this? Okay, when we differentiate t squared, we will get 2t. Okay, so yeah, integration. Yeah, we know what is f of t. We know f of we can say f of t, okay, equals to t, or maybe to make things easier, 2t, right? F of t equals to 2t. Why do we want 2t? Because when we differentiate t squared, we will get 2t. We will not get t, we will get 2t. So that's something to pay attention over here with regards to t squared, t cubed, all that. Okay, so we will need to take note of this factor of 2. Every time you differentiate, you will have all the powers being brought down, so to speak. So f of t will be equal to 2t. So let's just substitute that in. Wherever you see f of t, you'll get 2t, not t. Okay. So yeah, there will be something we'll need to change. Okay, every time we do that, we will need to change. Okay, so we'll be doing Laplace transform of 2t, not t. So integrate 2t dt, that will be just t squared, right? That will be just t squared, because that's what we want. Okay, Laplace transform of 2t. Well, we can just bring the 2 out. We can just bring the 2 out, and we'll just have 2 Laplace transform of t. 2 times the Laplace transform of t. Okay. And this thing also same idea. You will have a you will actually evaluate t square at t equals to 0. Alright, so that second one will be 0. And then you will have what? 1 over s squared in the inside. So let's do this. Fraction 1 over s squared. Okay. Then you have fraction 2 over s cubed. Okay, so this is how you do Laplace transform of t squared. Then you can keep doing this, right? You keep doing this. So yeah, you just keep doing this, and you substitute it right. You will be able to get Laplace transform of t squared, t cubed, t fourth, all the way through, however many times you like. Okay, so yeah, hopefully this gives you an idea of how to do this Laplace transforms of derivatives and integrals. Okay, and this thing we'll actually use to derive the Laplace transform of t and the Laplace transform of t squared. That's what we saw in this video. So thanks for watching.